Now, number 8. A double bond is treated as one electron pair when determining the electron pair geometry. And that is true. The reason for it being, for example, let's take a molecule that has a double bond. I'll take one of the resonance forms of sulfur trioxide. Now, when I'm counting the electron pairs, the double bond, when we're determining electron pair geometry, we're interested in the repulsive effects of the electron pairs that are in the covalent bonds. Now, and they're going to have a geometric impact of trying to get as far apart from each other as possible because of the repulsive interactions. And so the molecular geometry we're expecting to observe is the one that gets them as far apart as possible. Well, with a double bond, these E pairs, or these bonding pairs, are localized, the double bond, between the sulfur and the oxygen. So that's a double bond situation. They're not going to drive each other apart. They're going to act as one single bond. It's going to be the same, it has the same geometric impact, this double bond, as this single bond, as this lone pair does. So we would say this has 3 E pairs when we're determining the electron pair geometry, and it would predict that we have a trigonoplanar arrangement of these pairs, and indeed that is what is observed, and we get a bent molecular geometry. Another example would be carbon dioxide. Here I've got a double bond and a double bond. If I treat these as an individual pair, there's 2 E pairs. The geometry that minimizes the repulsion is going to be the one that gets them 180 degrees apart. So this is the linear geometry that is indeed observed with carbon dioxide. Okay, and that is, this is easily seen when we treat the multiple bonds as a single pair, because they're constrained to be in the position between the 2 atoms. And that's why that is true. That was number 8. Double bond is treated as one pair. Okay, number 9. In the valence bond model, all molecules are diamagnetic. That is true. Well, I could say that as long as we have an even number of electrons, but it is one of the defining characteristics, and why it's so important is the Lewis model and the valence bond model gives us so much information. We need it. It gives us all this geometric information, allows us to understand the polarity of the bonds and the polarity of the resulting molecules. But what it doesn't reveal is, and because by the very nature of the hybridization and the way the bonds are put together, all the bonds are formed between pairing of electrons from different atoms. And so I get molecules like nitrogen, which successfully is predicted to have a triple bond, and I have oxygen, which successfully is predicted to have a double bond. All of these electrons are paired. They're represented as pairs. The Lewis model, the valence bond model, I have bonding pairs and lone pairs. That's it. And so that doesn't reveal whether there are indeed unpaired electrons. And in fact, nitrogen is diamagnetic, as observed. You pour the liquid nitrogen in the poles of a magnet, it keeps going, whereas liquid oxygen is paramagnetic. You pour it between the poles of a magnetic field, and it will hang in space. And that is not revealed. There is no distinction between that with the Lewis dot model, because I'm assuming everything I represent them as pairs, the bonds, and the others dots. And now we can also look at oxygen over here and see within the molecular orbital approach that because I follow Hund's rule, this reveals immediately that the presence of two unpaired electrons. So oxygen is a diradical. It explains a lot about its reactivity, but also explains that it is paramagnetic. I have two unpaired electrons. And so we need the molecular orbital theory to bring out this feature, which is revealed clearly here and simply, but not revealed with the Lewis dot model. So I will take that statement as absolutely true. Number 9. Sort of one of the defining features and the reason we have to have the other approach. Okay, number 10. All molecules with polar covalent bonds are polar molecules. Well, that is obviously not true. And a good example here can be found in water, where I have an electronegativity difference between 2.1 and 3.5. So I have a dipolar bond here and a dipolar bond there, and these dipoles add vectorially, and plus there's a little-bitty dipole here with a lone pair effect, which points in that direction. And we add these vectorially, and I end up with a net dipole that is observable, and water is indeed the quintessential polar molecule. The same could be said for nitrogen, for ammonia in this case. However, with carbon dioxide, I've got a difference between 3.5 here and 2.5 on the Pauling electronegativity scale. So I have a dipole pointing this way and a dipole pointing that way. And so these dipoles add vectorially, and the molecular geometry is such that these dipoles cancel each other out. And this is a non-polar molecule, and it is observed that to be that way. So that means that statement 10 is false. Okay. Now, number 11. An atom with trigonal bipyramidal E-pair geometry must have sp3d hybridization. Yes. The hybridization is dictated or by the E-pair geometry. That's the hybridization, is the mixing of the orbitals that will give rise to that particular geometric arrangement of hybrid orbitals and trigonal bipyramidal, which is I'm going to have one little hybrid orbital facing this way, another one, let's see if I can draw this. Another one going that way, the axial positions. I've got one coming out of the board and one going into the board, and then one coming out of there. So I have a trigonal, although it's not a very pretty picture, trigonal bipyramidal E-pair geometry. I would create hybrids, each with one electron in it, ready to overlap with other atoms, which can pair up and form covalent bonds. So I have this is a trigonal bipyramidal arrangement. This can only be found or created out of by taking s orbital, an s orbital wave function, mixing in all three of the p orbital wave functions and one of the d orbital wave function. So this is going to be sp3, sp3d, and I have 1, 2, 3, 4, 5 resulting hybrid orbitals, where I have 1, 2, 3, 4, 5 pure atomic orbitals. So the number of orbitals that mix together has to match the number of orbitals in the hybrid, the resulting hybrid. So sp3d, yes, is indeed required. So that is, which one is that? That is number 11. That is true. Now, the number 12. The bond order in the O2 plus cation, the dioxygen cation, is higher than the bond order of the O2 molecule. This is indeed true. And this we're going to have to look at our molecular orbital approach here. But this is the O2 molecule with the electrons occupied. I start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atomic orbitals on each oxygen. I end up with an O2 here. And I have I place the electrons into the molecular orbitals following Hund's rule. I end up with these last two in the highest unoccupied highest occupied molecular orbital. The highest occupied molecular orbital being a antibonding, the pi 2p star antibonding orbital. Since I'm removing now that is going to give me a bond order that's 1/2 8 minus 4 equals 2. I have a net double bond. What happens when I remove one of the electrons? We're going to remove the one that's most easily removed, which is going to be the highest occupied molecular orbital, so I'm going to get the O2 cation, at which point I'm removing an antibonding electron. Therefore, I'm going to increase the bonding interactions and decrease the antibonding. I'm not increasing the bonding interactions, but I'm decreasing the antibonding interactions. So I have it's 8 here minus 3, which is 5 halves, and 5 halves is greater than 2. Since I had to decrease the number of antibonding interactions with the same number of bonding interactions, so I removed an antibonding electron, I see an increase in the bond order. And so the resulting bond length in oxygen plus cation, O2 cation, is going to be shorter. And it's going to be stronger than the corresponding bond in the dioxygen molecule. So this is indeed true. This is problem number 12. Is true. Now, for number 13, the valence orbitals within an atom mix together to produce hybrid orbitals with a geometric orientation that minimizes the repulsion between the electron pairs that occupy the orbitals. That was a mouthful, but it was basically a statement of what happens. It's the E-pair geometry that's going to result is the one that minimizes the repulsive interactions. Why is that so? Well, because they're all enveloping the central atom. And when we're discussing the molecular geometry, it's going to be the way these electrons, which have to envelop the central atom, are going to be arranged in space to keep these electron pairs, which are forming. When I say pairwise, it's taking one electron from the central atom, pairing it up with another electron from another atom to form a bond. So these bonding pairs are going to get as far apart as possible from each other. And that repulsive interaction is going to drive them apart, and also the lone pairs associated with the central atom, which are going to be spatially extended beyond the atom, but they still envelop the atom. So this is just another way of saying that with a lot of words, but yes, number 13 is indeed true. Number 14. If an electron is removed from an anti-bonding orbital, the bond order is reduced in the resulting molecular ion. Well, that is absolutely false. If I'm removing an antibonding orbital, I'm going to be reducing the antibonding interactions while leaving the bonding interactions the same number of bonding electrons. And so it's going to, like as we discussed with oxygen, that is going to have the opposite effect. It's going to increase the bond order, not decrease the bond order. So that is false, number 14. These questions are intended to check and test your comprehensive understanding. And so I often ask the same thing from different points of view. So you have to think, slow down and think about what the question is asking. Now,